Okay. So here, I have kind of, essentially, this is the cheat sheet I used when I did my exam. You can notice there's a bit of open space here still. I just never ended up filling it up. Considering you guys will have more topics on your final than I did, it'd probably be best if you added additional notes. But the general concept of this cheat sheet is just that I have all the pseudocode for pretty much every function. And that helped out a lot for me mainly. Probably the most important thing for your cheat sheet is red-black trees. Specifically the delete function. Make sure, above all else, you have the pseudocode for delete. Alright? If you have found a way to kind of find a strategy for how to do red-black deletes, that's nice. But just have the pseudocode as a backup, because chances are, if you make one little mistake in a delete function, the entire answer will end up being wrong. And you'll probably have to do the whole thing all over again. Or you'll just end up getting the wrong answer. So, yeah. Oh yeah, I should have mentioned this first. You will not be given a cheat sheet like how we did it last with the actual midterms. This time, you'll be making your own cheat sheet. So this time, you are expected to actually craft your own cheat sheet. It can be typed. You can have pictures on it. You could have examples of problems on it. That is all perfectly fine. Just to let you know that we will not be giving you one this time around. Alright? And, yeah, it is one page front to back. Yeah, so just know that. Red-black pseudocode is good. If you need the linear time selection pseudocode, that is also a good idea. Make sure you have time complexities. That is important, because you will have time complexity problems on the exam. And make sure you have the procedures for strongly connected components. That is also really important. I don't have it on here because that wasn't on my exam, but you guys will have that, so make sure that's on there. We have 3 algorithms we need to deal with. Number 1, we use the linear time selection algorithm to find everything. Number 2, using a BST, we'll find the smallest element called the successor function. Number 3, using an RBT, we do the same thing as an A2. Okay, let's check our assumptions. We are assuming that we are using the sorting algorithm with the best worst case TC. So aka it's just saying use merge sort for A1. Okay. And we can ignore the time complexity of building a BST or RBT in A2 and A3. Okay, so we can ignore the fact that we're building, and that's important because building takes a ton of time. I believe for both BSTs and RBTs, building will take n log n time, but because we're ignoring this, we don't care about the fact it's getting built. That doesn't matter to us. Alright? So that's important to know. Alright, with all that said, which algorithm would I choose to solve this problem and why? Okay, so first off, we need to figure out the time complexities of this algorithm. So we're going to check A1 first. Now the important thing about a linear time selection algorithm is its time complexity, and I feel that it is self-evident as to what the time complexity is. So I'm just going to write that, and I think we can all safely call it for that, alright? I don't think there needs to be any more on that. A2. Okay, here. We're building a BST. So the BST is already built, right? We're ignoring that part. We're just going to try and find the smallest element in it. So I'm just going to quickly reason this out. So let's say this is technically a BST, alright? And I wanted to find, I don't know, what, the smallest element? That would work in this case. But I can reason it another way. I want to find the smallest element. 6, 4, 2, right? 1, okay? I'd have to go through 8, then 6, then 4. I see 2, but I have to go through it. I see 1, and there's nothing left. Because of that, I have to come back up to 2 and be like, oh, hey, that's the second smallest element, and I call it a day. The point is I have to basically go through the entire BST to even get to that point, which is annoying, so that proves that, you know, even to just access the smallest element, I have to call big O of n. So there's that. And then what? There's A of 3. This one is kind of the same as a BST, except as it ensures that it's balanced. Meaning I'd have to, like, if I took the thing from last time, I don't know, let's make it into some random BST. I guess it's like this, something like that. Oh, well, whatever, that's similar enough. And then if I wanted the smallest one, I mean, it's a lot easier to go through because it's actually balanced. You know, I don't have to spend as much time. RBT is pretty much always confirmed to be log n, and BST is pretty much always n. So there we go. We have our time complexities for A1, A2, A3. The question is, which one should we use? It's pretty easy which one we should use. Use A3. And we have to answer why. And so when they say justify your answer, most likely they're wanting to know why you are planning to use, you know, A3, right? You can just say, you know, lowest TC, lowest time complexity. If you want to go a step further, you can explain why it's the lowest time complexity. RBT ensures, I don't know, RBT ensures balance equal big O log n, log good. That's probably the fullest extent you need for getting the justification points. Where does the second part of the statement come into play about calling the successor? So I'll give you a BST, right? I don't know, like 8, 4, 11, 5, something like that, right? Okay, here's the thing. I want to find, the smallest element possible. To do that, I'm going to go as left as possible. That guarantees the smallest element. So I find 4. Once I have done that, right, and doing that, by the way, the biggest n time is going to be n, right? Because I could have a tree where it's like 8, 7, 6, 5, right? I want to find the smallest one. I got to go all the way down, and I have to pick 5. That is big O of n by default. When I go on and call find the successor method, the reason why I call the successor method is because the successor must be the second smallest element of this entire thing. That is why I call successor. So I'm going to call successor on 5, and I will end up getting 6. 6 will be my answer, right? And that's why. Because 5 is no children, so I just have to take, you know, what is its parent, which is 6. Because of that, 6 is the successor. If we wanted to make this longer, I could do, like, I don't know, make this a 0 instead. And then just make it like 1, 2, I don't know, like, let's see here. I have to do, I'm trying to think about how this would go, like 5, 4, 3, 2, 1. So the point of the successor method is, you know, I got 0, and then I go right once, and now I have to go all the way left, which is still going to basically be the entire array in a BST, because this is perfectly legal. You can do this. This is allowed. So that's essentially where the successor part comes in. But the idea of the successor function is it takes just as long as, like, say, just actually finding the smallest element. So you could say it's just this for both of those, but that just, or sorry, not for that one. You could say it's that, and then you could say this too. But the idea is it's just, you know, it's just 2 times our big O, which, you know, constants don't matter. So you don't really have to consider it. Longest common subsequence. And surprisingly on this one, normally when you do a longest common subsequence problem, it kind of like looks obvious. Like, an example I did in my recitation is like, I believe it was, oh, is it not writing? That always happens. Come on. Nope, it's not writing. It does not want me to be able to use that. Alright, we're gonna have to back up with this. I don't know, God, this is so much worse. Okay, cat versus, I believe it was katsu. I did that, and when you look at these 2 words, it's pretty obvious what the actual, or no, it was cats, sorry. It was pretty obvious what the actual answer would be as to what the longest common subsequence was. It's ATS, right? Because you can see ATS in both words. In this case, it's not so obvious. There is actually a longest common subsequence here, but it's just not showing. So we're going to actually have to figure out what that's going to be. First off, I'm going to write X on the left, A, B, C, B, and I'm going to write 4 zeros next to it, right? Once I've done that, I'm going to now write the Y up here, B, D, C, A. Then I'm going to give it 4 zeros. Notice these zeros do not actually intersect in any way. If I were to draw a line, they won't ever touch each other at any point. So that's the important thing, right? Once you have done that, everything in the middle, this middle space here, that is going to be where our actual table resides and where we can actually, figure out what we need to do. All right, now follow through with me. Every time I look at a little table slot, I am going to compare the left number and the top number. If they are the same, I'm going to assume the top number. Now with that said, I'm going to compare A and B. They're the same. So I'm going to assume the top number, which is going to be 0. And on top of that, I'm going to place an arrow that points towards the top number, indicating which one I chose. Good. I'm going to go to A and D. Okay, same thing. I'm just going to do that. And I'm going to do that, right? Now, we're going to notice I'm going to hit A and A. They are the same letter. Because of that, I will increment whatever number I had previously by 1. So I'm going to do that. And no matter what, I am going to put it northwest. I'm going to put a northwest arrow. I don't care, what left or top is, I'm just putting a northwest arrow. I'm just going to fill out the rest of this table then, and I'm going to see if you guys agree. This should be pretty quick. So I'm going to do 1 left, 1 up, 2 northwest. That's not a northwest arrow. Okay, 2 left, 2 northwest, 2 left, B and C 2 up, and B and A 2, I believe, up. Yeah, that's right. In the second row for B and A, Y left. Oh, because I'm a moron, that's why. Thank you for that. Okay, cool. So when you're incrementing, because you have like a number or a letter and a letter that are the same, you have to do it in reference to the diagonal. I forgot about that. Sorry about that. So in this case, this can't be happening. It has to be a 1 instead. That makes more sense. And then this has to obviously be a 1, and because they're the same, it just points upward. That would make sense. Okay, no, you guys are right. My bad. Let me make sure on that. So what, this is a diagonal. That makes sense. This is a diagonal. That makes sense. I think those are the only ones. Oh, wait, well, this is a diagonal. That makes sense. Okay, good. Phew, all right. We're good to go. All right, now I think the table is good. Is that table good? Okay, cool. So part A of this question would, on the actual exam, would be like, hey, this is the table I want you to give me, right? And then and I think it's gonna literally, the answer sheet will be like, I'm gonna give you a bunch of like slots with like word, and I want you to literally fill in the blanks. So that's probably what the answer sheet will look like, if I remember right. So there we go. And then that's part A, right? Part B is going to probably just ask, what is the least common subsequence? Like, what can you actually get the least common subsequence after you've done this graph? And the way to do that is pretty easy. Start at the bottom right always, okay? We're going to start there. I'm going to draw in red for this. We're going to start at the bottom half, and we are going to follow the arrow, which direction it points. So this one points up, I'm going to go here. This one points left, I'm going to go here. This one is a diagonal, so I'm going to record whatever letter showed up, which is C. Okay, now it says to go northwest. I'm going to do that. This one goes left. I'm going to do that. This one's a diagonal. I'm going to write that, and it says to go here. I just hit the top left of the graph. Or not the top left, but like these zeros where they are not, like, they're only with one word. If you touch any of those, you stop counting. So I just hit that 0 up there. I'm done. and this is my least common subsequence as my answer. Okay, where is BC and BDCA? See, this is the thing I'm talking about, right? BC is not actually in BDCA. Despite this, it is actually still a subsequence, surprisingly. Because a subsequence does not mean, hey, I just need like words that are in consecutive order. A subsequence means, hey, I need like words that can show up in order. They don't have to be next to each other, so I could be like B, Z, 1, 2, 7, 8, 5, and then a C. That would still count. I would just X out all these words. I would just ignore all those letters. They don't matter to me. Right? The point is that B showed up first, C showed up second. That's what's so important about the least common subsequence, and why, just because you look at the words and they don't look like they actually have, like, you know, letters together, the same letters together, that doesn't mean there's not a subsequence. Do we write the subsequence in reverse orders? Yes, write it in reverse order. So you noticed when I did mine, I started at the 2 up, then the 2 left. I saw this diagonal, which has C, so I wrote C last. Then I take the diagonal, I go to the left, I see another one, and I notice that it's B, so I write B before C. Then I went to 0, and I hit one of the zeros. Let's do 3A. Got that there. And we are going to just assume it's empty. Okay, so it's going to be... we have a hash table with 4 slots. I'm just going to draw that up front, which is going to be some 4 slots. Okay, cool. We're using open addressing. I will box that in an easy to see color. And we're going to have our hash function up there. We are going to assume the hash table starts empty. That's cool. I'm going to write nil and everything. This is important. I'll show in a second. Alright. And I'm going to say j is equal to 1 for A. So that means that my h, k, comma, I is just going to be k plus 1 times I, which is just I. That's good to know. Alright. Now, show the result after inserting 3, 7, and 11. Okay. So we're going to have to insert 3, 7, and 11. Now the way I'm going to do this is simple. I'm going to use the hash function to insert every number. How will I do this? I'm just going to write h. I will replace k with whatever number I want to put in, so 3. I will replace I with 0. Always. I will always start I with 0, which is just going to be 3 plus 0. Okay, now that I've done that, it says up here I have to do whatever I got there mod 4. Like this, which is just going to be the same thing. That doesn't change. Okay, now this hash table has indexes, which is I is equal to 0, 1, 2, and 3. Whatever I get out of my heap function answer is the index I will be placing my number into. In this case, I got 3, so I'm going to replace nil, and now I'm going to put my data value 3 in there. Okay, sounds good. Now that I've done that, I'm now going to try and insert 7. So I'm going to do, what, H70, which is going to be 7 mod 4, which is 3 again. So I'm going to try and put 7 into 3, except 3's already there. Now I'm doing open addressing, meaning I can only have one number at a time in a hash table slot, meaning I can't put 7 in there. So how am I going to do this now? The way I'm going to do it now is I'm now going to, this is where I comes in. I now have to call h7, 1, which is going to end up being 7 plus 1, which is going to be 8. Oh, that sucks. 8. And then modded, I'm going to have to do mod 4 is going to be 0, right? And now, what this means is I can actually, how do I, okay, oh god, okay, there we go. I can actually remove the nil here because I got 0, and now I'm going to actually be placing 7 in this slot, right? And when I then call H on 11, 0, that will fail because that will go to 3, 11, 1 will go to 0, so I have to do 11, 2, which ends up being 1. And I will then be able to place 11 inside the index 1. As so. Man, this is a lot more slow going without the pencil. Alright, there we go. And there we go. That's how you would do A. Anyways, I just deleted 7. Now, one thing to note, this is probably something that could screw you up. You don't, when you delete something, you don't replace it with nil. Using the pseudocode we were given, you actually have to replace it with deleted. I'll just say del, because I'm actually very physically limited with this right now. So you have to say del instead. So keep that in mind. But other than that, it is pretty simple. You just delete the number 7 and that's it, right? You would answer with that. So that would be the answer to B. And if I were to do C, it says I need to insert 15. So I'll just write C here. For C, I would just have to say, H of, 15, right? And then I know that 15, 0 is going to fail, because that would result in 3. I know, but when I do 15, 1, it will work, because that will end up equaling 0. And there's only a delete in there, so I can just simply replace that delete with 15. And that would be it for question 3, ABC. You have to get to D, which is a bit more complicated in this. So, what could J be in order to make the probing work properly? So how will we do this one? So again, we're going to have the 4 slots. This one isn't really in reference to, the actual data we got. This is more so asking, can J be literally, out of the 3 J values we were granted, what can J actually be with those to be able to access all slots within the heap, or within the hash? So I'm going to write here, J, the set was 1, 2, and 3. Alright, that's good. And the equation, H, or KJI, was equal to K plus JI. So using these two things, which J's will allow us to probe everything inside the hash. So we already proved J is equal to 1, because what we can do is every time we just stored we stored 3, 7, and 11, we did this. And if I were not to delete 15, right, then 15 would just end up being here, because we can always just increment by 1 to fill up every slot. So J equals 1 already works. We confirmed that. Now, the next one I want to confirm is J is equal to 3. I'm going to do that one next. So let's just get that out of the way. And so the idea is we're going to have HK3I is going to be what? Whatever, K plus 3I. That's what we're working with here. So I'm going to make another thing here, 4 slots. And I'm gonna try, yeah, that'll work. 3, 7, 11, 15. I'll try putting all these numbers in. And hopefully, by putting these 4 numbers in, I should be able to fill up every slot within the heap. So I'm gonna do that right now. Or rather, I can make this even simpler. I could just say, I'm just going to keep putting in the number 3 over and over and over again. And if I can fill this entire hash with 3, I'll be good to go. So, let's try it. I'm going to do H of 3, 3, 0, which is just 3, which is just 3 plus 0, so that's just 3, so then I put it here. Okay, cool. I'm going to do that again, right? Because I already put in 1, 3. I'm going to do that again, but it'll fail, right? Because I already have a 3 in here, so I can't do that again. So I'll have to do H of 3, 3, 1, which is 3 plus 3, which is 6. Mod 4 is 2. So then 0, 1, 2, I have to put 3 in here. And you can notice the pattern. If I do it again, I probably have to do 3, 3, 2, which is 3 plus 6, which is 9, modded 4, which is going to be 1. I put a 3 here, If I do H333, that's just going to be 0, and I can put a 3 in here. J equals 3 works. So we can confirm that 1 and 3 will actually be able to probe every single memory slot within the hash, or memory spot. Does that make sense? Okay, let's move on to j is equal to 2, and we'll see this one. And since you saw the visual example of that, I don't want to do it again, so I'm just going to literally write this. Remember, this 3 here is some arbitrary number I picked just to be like, oh, okay, this can show the mod. So what I'm going to do is equal to 3 plus 0, so that's 3 again. Good to know. 3, 2, 1 is going to be 3 plus 2, which is 5. Modded 4 is 1. Okay, I got 1. 3, 2, 2 is equal to 3 plus 4 equals 7. Mod 4 is 3. I gotta repeat. That's not looking good. 3, 2, 3 is equal to 3 plus 6, which is 9. Mod 4 is equal to 1. So it seems to alternate between 3 and 1, meaning indexes 0 and 2 are never hit. I could keep going on with this, but I get the feeling that it's just going to keep hitting 1 and 3 and over and over and over again, and I'm not going to end up being able to get indexes 0 or 2. So I'm just going to call it quits here and just say J cannot be 2 for probing. So with all that, the final answer is going to be J will equal 1 or 3 if you want full probing for the hash table. Alright, and that's how you do number 3, I think we're on. Let T be an empty red-black tree. If we insert 1, 2, 3, and 4 sequentially, then draw the tree after insertion. Cool to go. Like, if you do insert, it should just be like, hey, okay, if Z key is less than the X key, then X dot left, else on the right. Okay, yeah, there you go. That proves it right there. Alright. You would want to use the RB insert I have up here instead of the tree insert. I think that's something else. But for the RB insert, it is just like, if the key is less, only then it goes on the left. If it's equal to or greater than, then it goes on the right. So if we were to do 2 nodes with the same key, the second node would go on the right of the first. That's what would happen. Like, so I'll just draw it up here for future reference. If I got 2, I would have to put 2 on the right. Okay. With that out of the way, let's have some fun. So we're gonna do empty red-black tree, put in 1, 2, 3, 4. Alright, so first off, I'm going to insert. Every time you insert a new node, it's red. So I have 1. Now the problem is the head can't be red. So I have to switch it to white. So I'm going to do that. Okay, cool. Now I'm going to insert 2. Okay, 2 is bigger than 1, so I put it on the right. Alright, that's it. This doesn't seem to break any general rules, so we can just move on. It is a white-red tree. And next I'm going to do 3. 1, 2, 3. Alright, and then I'm just going to go on and connect that. That seems to be a slight issue. I don't think that's allowable because we have 2 reds in a row, not allowed. So we're going to have to deal with this accordingly. Now, how are we going to do fix-up? The important thing about fix-up is you track a multitude of things, right? Your X is going to be, say, on the bottom here. You're going to track X's parent, X's grandparent. Oh, shoot, I wrote that wrong. Like that. Okay. And you're going to track one more thing, X's uncle. X's uncle is going to be found like this. You're going to go to the grandparent, and whatever child the parent is, the uncle will be the other child. So this nil node, because nothing was there, that will be X's uncle. Is that making sense? These are like guaranteed definitions of parent, grandparent, and uncle, which, now that I think about it, you guys already did assignment 4. I'm sure you know how to do this. But this isn't the case if you accidentally completely lucked into getting the right answer, or if you got the wrong answer on that assignment, right? So now that you know this, right, what do we have to do? There are 3 scenarios that are dependent on the uncle's color. Now, if the uncle is red, then we'll get to that. That'll show up later. If the uncle is black, then what we next have to look at is the position of X, okay? And there are 2 cases. X will either be the right child or X will be the left child. In this case, X is the right child. So uncle is black and X is right. This is case 3. Now I'm going to call it case 3. So in case 3, what happens is I need to do a rotation, right? A rotation based on the orientation of my current red-black tree, which means in this case, because there's a lot more numbers on the right, I'm going to be doing a left rotation on the grandparent and the parent. So I'm going to do that. And first off, I'm going to write it underneath here. I'm going to write the numbers after rotation, which is just going to look like this. I guess I'll write the nil too, why not? Like so. Once I have done this, I am then going to switch the colors between the grandparent and the parent. And now it'll look like this. And I'll get rid of the nil, it's not useful anymore. This is what if the left child was red. You're about to see that in a second. So this is what the red-black tree will now look like. And this is a perfectly good red-black tree. So I now can insert the final node 4. I'm going to do that now. 4 is bigger than 2, it's bigger than 3, so it goes here. Okay, so now you can notice I have 2 consecutive reds, not allowed. I have to do something again. So I have to first check the uncle, right? The uncle is red. So now I have to do a different case. I call this case 1. In case 1, all you do is you change the color of the parent and the uncle. So I'm just going to make these white. And that is it. I am not doing anything else. And now it's a full red-black tree, and I inserted everything, and I am done. And that was the problem. That's how you do it. So this is case 2. So if 3 is on the left, right, and I'm going to keep this, I'm going to say what's X, what's the parent, what's the uncle, and what's the grandparent. Right, I'm going to say that. Okay, in case 2, the scenario where 3 for some reason showed up on the left, oh yeah, you're right. I'll change that. You're right. Sorry about that. My bad. Oops. No. Get big. Okay, cool. Let me fix that so it is a BST. My bad. There we go. So in the case where for some reason you have a child on the left, right? X is on the left, and you have it look like this. I am now going to have to do another rotation, but this rotation is going to be different. Previously, I did it on the grandparent and parent. This time, I'm going to do it on the parent and X. And based on the rotation, based on the, not the rotation, the, how it looks, right? I forgot the word. Based on how it looks, which in this case, it looks like it's left heavy, I am now going to have to rotate it to the right. So it will end up looking like this when I write it. It turns into this. So I have nil, I have 1. And then I'm going to have 2, and then I'm going to have 3. And what you'll notice is it kind of turns into like what we had up here when we did the problem. And the reason is because the idea of case 2 is case 2 should lead into case 3. That is the point of case 2. It is supposed to lead into case 3, right? So cases 1 and 3 should result in a completed RBT, unless if another thing shows up. Case 2 should lead into 3, right? Which is what ends up happening here, and then I have to do the exact same thing, and then it ends up working. Hooray. Hoo-ha, the whole world works. We got eyes 10. That's awesome. okay? And it's going to be so it says 1 and 25, meaning the array is going to look like 1, 2, 3, 4, ... all the way to 23, 24, 25, that good stuff, right? Okay, so that's what the array is going to look like, because we pick from index 1 to index 25. So we have our array. Now, the thing about it is, what is the largest possible value of, say, pivot X, right? If we're going to work with this. So, apparently what happens is, for one, because we're doing one index, you have to do what? You have to, instead of taking like the 10th element, you have to do 10 minus 1, that element, which is our 9th element, right? Okay, that's good. That's fine. Now, the only thing you have to do is either pick the 9th element from the start or the 9th element from the end. So the smallest one, S, is just going to be 9, and the largest one is going to be 25, I believe, minus, or no, 25 counts. Like, that one counts, so no, not 25. It'll be like 25 minus 9 minus 1, which I believe is 17. And that is your answer. So I got that graph. I need to do a top sort for it. So I guess I'll just write it here because it's nicer that way. Okay, cool. Okay, so write down all the topological sorts. So the way you want to do a topological sort is if an arrow is pointing at a letter, right? That means that that letter has a prerequisite that needs to be filled. So for example, B has has two prerequisites that has to be filled, which is A and C. D has two prerequisites that needs to be filled, which is A and C, because two arrows are pointing at D. Now let's check A. A has no prerequisite. C has no prerequisite. Okay, so we've gotten that. The concept is whatever has no prerequisite, you can write at any time. Whatever does have a prerequisite needs those fulfilled before it can be written. So let's do the topological sort for this one. I'm going to do, first off, I can choose A or C. So I'm going to write them both alongside each other, right? Because none of them have any arrows pointing to each other. So once I've chosen either one, I'll notice that B and D still needs one prerequisite resolved from the other. So I have to write it as once I pick A, I do C, or once I pick C, I do A. Like so. Once I've done that, I am now free to choose B or D, because both of their prerequisites have been fulfilled. So I have to account for both of these scenarios. Like so. And so now, I'm going to write either B or D. So I'll write B first, D second on both of these, and then D first, B second on both of these. Like that. And that's how you do a top sort problem. Okay, so we need to write down all the strongly connected components of the given graph G. Okay, now one major hint for a strongly connected component is if there's a cycle in the graph. Basically, if you can go in an infinite loop from node to node in the graph, that's pretty much a cycle. So the obvious one is CE, right? And then the rest of them don't look like they ever become a cycle. So if you wanted to answer this question super quickly, that's pretty much how you'd answer it. Just like, oh, C and E go in a cycle, nothing else does. There you go, that's an SEC. Now, bear in mind, this is not the only answer. Just because C and E are the only cycle does not mean they're the only strongly connected component. They are one of them. Because if a vertex doesn't have, if a vertex is not involved in a cycle whatsoever, you have to write it by itself, so like this. Because that technically counts as a strongly connected component. So bear that in mind, right? Just because, I'm going to write that C better, just because, oh my goodness, just because they are not in a cycle does not mean they would not be included in the answer. Kind of like a self loop, kind of. But the point is just like you show that they are like by themselves within an SEC. Like there is no other component connected to them. They don't have a self loop explicitly, yeah, which is kind of more like when you write it by itself, it's more like A is all by itself within its own kind of strongly connections, meaning that A is not actually connected to any other components strongly, right? A is by itself. That's what it means. So, but these nodes by themselves do count as an actual answer to the SEC. So bear that in mind. All right, now that's a short way of figuring out all your SECs. The problem is because they asked B, we can't just do the short way and call it a day. We actually have to do the long way of doing it, which is a process and takes a while. But this, I believe, would be the answer to A. Why am I not writing C? Because C and E are actually in a cycle. A strongly connected component is when you can actually traverse through nodes and go in an infinite loop. You can notice C points to E and E points to C. So I could go CE, 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 CE over and over and over again. That means they are strongly connected components. So that's why C and E are not individual. On the other hand, if I tried, like, I don't know, I go to A, I have to go from A to B or A to D, and I can't go anywhere else. I can't ever get back to A. So A is by itself. And that would be that. So C and E are together because I can actually do an infinite loop. So on the exam, yes, you do need to account for the individual ones, or else you will lose points for never mentioning them. So make sure you do account for them. Meaning you actually do have to know what the SECs are. So make sure you know that. So that was a short way of finding SECs, and because of B, because they mentioned B where we have to do all that text, we're actually going to have to take the long route of doing this. So let's take a look at B. Suppose we call SEC. When we call DFS G to the T, if we start at A dot D is 1, A dot F is 2. If X dot D is 3, what node could X be? And note that they were not performed in alphabetical order. Now you might be wondering what the hell does that even mean? Like, what even is that? What am I looking at? And I'm going to go over that now. So, the way you do SEC, the long way, the official way, is a multi-step process. So, 1, DFS on G. Okay, that's fine enough. Once you've done that, 2, DFS on G transpose and do it in order of decreasing finish times. And number 3, whatever has a non-nil pi is in an SEC with multiple elements. So that's the 3-step process on how to find an SEC. The last 2 sound super difficult, so we're just going to pretend that doesn't exist. Whatever ignores you can't hurt you. And we're just going to start with number 1, which is just the regular DFS. So I'm going to go on and take whatever graph we had originally, ACE, BD, and then I'm just going to draw that, draw that, draw that, draw that, and those are in a loop, right? Okay, so the first thing I want you to do is just give me a regular DFS, right? I don't care about anything else, just give me a regular DFS. And important thing, it does not need to be in alphabetical order, so I don't care how you do it. Just do it. Okay, now, the way you do your DFS is going to be very useful here, because this is asking, this thing says, hey, if we were to start at A, then A dot D is 1, A dot F is 2. This is for when we're doing the second step, right? So when it says something like this, what this means for our regular DFS is whatever A does, its finish time should be the biggest number. We need to do our DFS such that A has the largest finish number of all the nodes. So if you ever see A dot D equals 1 and A dot F is equal to 2, that means node A on your DFS should be the node with the largest finish time. And you'll come to see why in a second, but for now, just know that you need to do your DFS for that. So you need to start from a node such that A doesn't finish first. Someone in the comments mentioned, hey, start from C first. That's a good idea. That should work. So I'll do that. We'll start from C. So I'm going to say C is nil because I'm starting from it. That's a 1. Okay, I'll go to, I don't know, any letter. I'll do alphabetical because I feel like it. It says it doesn't have to be in alphabetical. That doesn't mean it's not. So I feel like doing alphabetical. It's easier to track, so I'll do that. I go from C to B. I discover B. B doesn't have any arrows pointing out from it, so that's nothing. B came from C. Now I have to do D, same concept. E points back to C, not really that useful, so same concept. And C is now finished. Okay, cool. Now I'm going to do A, which I discover here, and then I finish here, nil. Right? Okay, good. So I just did DFS on, all of this. Before I say anything else, are we all still good on DFS? Because I know we haven't really had to do it a lot in recent memory. But it will be necessary, and it will be really important to do for the future. Okay, good. So, now, we just did step 1, which just do DFS on G. Now we gotta do step 2, which I'll explain right now. First off, we're doing DFS again, but it's on GT, G transpose. So when I say transpose, what that really means is I'm gonna write the vertices exactly the same as before. The arrows will point the opposite direction they originally were. So we see A and B, A was pointing down to B. B will now point up to A. It's been reversed. It's the transpose of the original graph. So I'm going to go on and do all that. And C and E were pointing to each other, so it doesn't really matter. There we go. So now we have the transpose of this graph. Now that we do that, we're going to do DFS on it. So I'm going to go on and write D, F, pi, and then A, B, C, D, and E. Good to know. Now, we did that. It says, do it in order of decreasing finish times. What that means is now, instead of doing it in any order willy-nilly, now I have to do it based on the finish times in step 1. I have to do it in order of decreasing finish times, meaning I go from the largest one to the last one. So A has the largest finish time, so I have to start with A, no questions asked. And when I start with A, I discover A with 1, and I finish A with 2 because there's nothing A is pointing to. So A starts with 1 and A finishes with 2. That sounds pretty familiar. That sounds kind of familiar there. If you get to step 2 and your A starts off with D and F at 1 and 2, you are on the right track. Because that is what we have been aiming for when we did step 1. We wanted to do a DFS such that when we start step 2, A is like this. Yes, it's literally just reversing the arrows. That's what they mean by GT. Just reverse the arrows and then do a DFS on it. Alright, so that was the point of doing step 1, specifically like how we did. We did it such that we started with C so that we could complete B, D, and E before A ever was discovered. Now, it'll help us out because now step 2 is following exactly what they say with starting at A. This is what we want. Now it's asking if x dot d is equal to 3, which node could x be? So x dot d is equal to 3. So whatever node we have to pick next in step 2 is what's going to matter here. And in this case, C turned out to be the second largest finish time, so we have to start with C. So if x dot d is equal to 3, well, C dot 3 is equal to 3. So meaning C is actually a correct answer. There you go. By doing this entire process, we have determined that C is a possible node to pick in this problem, in this scenario in B. Now, I will warn you, C is not the only one we could have picked, right? This is one of them that we could have done. There is another entire possibility that we can pick here. So I'm gonna go on and write it on the right side, because if we already just proved C works. Because E is in the exact same as CC, E should work too. Because you can infinitely connect from C to E, whatever worked at C can make a pathway towards E. So I'm going to try that. That sounds like a good basis for it. So I'm going to start at E. E's 1. Okay, cool. Alright, I can only go with C, so C is 2, and it starts from E. Okay, what made me choose C first? Just intuition. The point was, I looked at this, and it said, if we start at A, we have AD is equal to 1 and AF is equal to 2 for the second step of the process. And the only way that could happen is if A finished last. And so I needed to find out to make a way to make this graph such that A is the last node I finish. And C was connected to every node except for A. So it just seemed like it was in the middle, it was connected to everything else, it just seemed like a pretty good letter to go with. So that's why I went for that. Let's go back to trying E. So I just did C. C has to lead to B, I guess. I'll just do that, that doesn't really matter. But I can't go anywhere from B, so that finishes. I go to D, doesn't really go anywhere, that finishes, so C has to finish, then E has to finish. We have 9 and 10 with A. Alright, A has the largest finish time. So if I tried doing, the inverse graph, clearly I would have this thing. A, B, C, D, E. Okay, A is nil. A finishes first again, and because E has the second most finish time, E would have to start with D equals 3, which is exactly what X wants. Meaning, E is also another possibility. So C and E are possibilities. Those are true. And now that we know that C and E, so you have to actually separately prove A, B, and D. But realistically, with those ones, you should just be able to take a look and be like, okay, those won't work. Because obviously A's not going to work because it's not connected to C or E. So I can't ever read those, so I won't finish last. B's not going to work because I could just pick A right after. D's not going to work because I could just pick A right after, and there's still other nodes to work with. C works because I've searched literally every other node but A. E works because I've searched literally every other node but A. Right? That's the idea. Alright, so I need to delete the number 2. That is leaving. First off, how am I going to do it? Now, the actual deleting of a number is not too hard, surprisingly. We won't need pseudocode for this part, so the idea is simple. We're going to look at node 2. If node 2 has no children, you just delete it and it's replaced with a nil. If node 2 has one child, you will replace it with its child and call it a day. If node 2 has 2 children, which is what is happening here, instead what we are going to do is we are just going to take its successor, and its successor will replace it. So that's what we're going to do. I'm going to go on and do that. And we're going to remove node 2, and we're going to put node 4 over here. But what? Okay. Okay, there we go. We have node 4. So now that we have node 4 there, we have to check what node 4's color is. If node 4 is black, something is clearly screwed up. And in this case, yes it is. So now we're going to have to figure out what the problem is. This is where we have to do delete fix up. And this is where I just can't be bothered with figuring out a pattern. And I'm just going to use the pseudocode because I don't know, because there's a lot of things that can happen at this point. So here is the pseudocode right here. Okay. So we first need to do fix up on whatever x is, and we're gonna feed in x as the 4 we chose to replace with, I believe. Right? I believe that's what the, oops, that's not it. I believe that's what the pseudocode says to do for the original, right? Whatever x is equal to, what? Y dot right. Oh, wait, is that right? X is equal to y dot right. And y is equal to the tree minimum. Oh, never mind. Oops, my bad. Nope. It should be equal to some, I believe, some nil on the right. If I could draw... Gosh, that's the problem with this. Okay. Okay, cool. Nil. Jesus Christ, this thing is dying on me. Ugh. Can you show a double black method as well? Hold on. I'm not really sure about the double black method. I really only know how to just follow. I just follow the pseudocode, and just check if it works. Normally the pseudocode is enough to determine if it will work or not, so. Oh, that's not good. Yeah, okay. I think it's... Okay, I'm gonna have to try, but I think this thing's about to hit the ghost. Alright, cool. So we have nil, which is some x. Oh man, it's barely responding. Okay. It's some x, right? So I want to go and... Oh my gosh. This is... Oh boy. Okay, so here we go. And now... I want to check if... Is it not a... Wait. Oh, shoot. Oh, wait. Hold on. I have to do something. My bad. Wait. I need to change windows. I just realized I was screen sharing the wrong thing. There we go. That's better. I wanted you guys to be able to see this. This pseudocode that I've been looking at. This is what I've been using. Okay. Now we can get back on track. So, the point was... X is set on line 11 in the RB delete on the top left. It's set in Y11 because we got tree minimum, and X is going to be set to Y's right. So because of that, X is actually pointing to X equals nil here, rather than where you might, think it'd be at the 4. It's just going to be the child's right there. Okay, so now that we have that, now we're going to check the fix-up function. So if x is the left child, it's not, so we don't care about this code. We're going to check the right. W is going to be the parent's left. So W is here. Okay, sounds good. W is always going to be the other child of wherever x is. If W is red, it's not. If W's right child and left child are both black, it actually is, so we'll work with this. Then we set W to red, and we set X to be X's parent. Okay, so we're setting W to be red. Interesting. And we set X to be its parent now. Oh, actually, this sounds like it makes sense. Wait, hold on. If I could just... whatever. It's doing the thing again. Whatever. Okay, X is the parent. That's fine. Alright. So now that we know X is the parent, X is on the parent now. Okay. And we specifically did, I believe, where was it? What line were we on? We did that. And then we set X to the parent. Once we do that, we make the color of the parent black. Okay. And it's already black, so we're done. that should be the results, and I believe, yeah, that's right. Yep, the slides say that's right. That's good to go. Alright, good. That's a deletion problem done.